airliner has an initial climb rate of 1,800 feet per minute until it reaches a height of 10,000 feet.
Okay, so we again have situations. This time it's a plane, and what's the plane doing? Ascending and descending. What's it doing initially?
It's inclined. It's
Climbing.
Climbing. What does climbing mean for a plane?
going up.
Right now it's going up. It may go down, we'll read further, but right now we know that that's going up. So underneath or underline the word climb, you want to, as you analyze these things, get a picture in your head of what's going on. It's going up, and then it gives us a rate of 1,800 feet per minute. And we know that's been helpful for us, Oscar, in figuring out our situation. So right now, you should have underlined climb and put a box around 1,800 feet per minute. Brody, are you with me?
Yeah.
You have 2 lines under climb and a box around 1,800 feet per minute?
Yeah.
Good. Identify the independent and dependent quantities in this problem situation. Explain your reasoning. Now, I want to remind you, a lot of times when we have this rate, something per something else, that's a clue to your independent and dependent quantities. And the per is kind of the divider between the two. So we're working with feet and minutes as the kind of rate of change this thing is tracking. Feet per minute. What is feet measuring?
Height.
Height, distance, altitude. Okay, how high up? And what is minutes measuring? Time that it's taken as it flies. So independent, dependent. Okay, who's the independent and dependent? And we will explain our reasoning. Who thinks they know? Jerry?
Is it the time that's independent?
Time often is the independent. If you have time, that's a great kind of giveaway. A lot of these problems, a lot of scientific research, a lot of stats, is measuring things that occur over time. So time, what's it getting measured in? Minutes. And what is changing over time? What depends on time? Altitude or height. And what is that getting measured in this problem? Feet. So we kind of incorporated 1 and 2. They wanted us to identify and figure out input and output values and units of measure. We did that both at the same time. Go ahead and sharpen your pencil. Okay, what it asks us to do too, and I wrote too big, so I'm going to use this space, is explain our reasoning. You guys did a great job of explaining, for the most part, reasoning, and I gave you points if your reasoning made sense. Okay, so why does height depend on time in this situation? Where are you at when you start in that plane?
On the ground.
On the ground. And then where are you at 10 minutes later?
In the air.
In the air. Where are you at 10 minutes after that?
Higher up in the air?
Higher up. Right now, all we know is that plane is climbing, so it's takeoff. Right? At time 0, it's on the ground. A little bit later, a little bit later, a little bit later. So changing over time, the height, let's explain. The height depends on how long it has been climbing. It may go up and down, but right now our situation is about this plane climbing. So how high up depends on how long it's been going. Okay, which function family do you think best represents this situation? We're talking about something that is changing over time. I can kind of see a little graph in my head. What kind of family do you think that is? Molly? Linear. It's giving us a rate, that 1,800 feet per minute, and all it says is it's doing is climbing. Well, Christopher said, I think the plane's gonna do that. For what it's describing is just the part of the flight where it's going up. All right. Down here in number 4, we're gonna sketch that graph. Most likely, because they told us that constant rate and they're only talking about climbing, it's one thing. I'm seeing a line that looks like this. There's my plane getting higher. Usually in graphs we put the independent variable on the bottom. Memo, what was the independent variable? Time in minutes. By convention, graphs have a title on each axis, and the units usually are shown. Oscar, do you have this graph? Okay. And then the dependent variable is usually on the y-axis. Anna, what was our dependent variable? Height or altitude in feet. All right, so up to this point, we are presented with a situation that looks a lot like the ones we've been working with in Chapter 1. Now, as we move over to page 75, here's where we're going to add to how we analyze this type of situation. Top of number 5. Somebody to read for us. Jerry.
Write the independent and dependent quantities and their units of measure in the table. Then calculate the dependent quantity values for each of the independent quantity values given.
All right, so let's take a look at this. We already know independent quantity is time measured in minutes. And dependent is height measured in feet. All right. Now, let's see. What do we know about this plane? Well, first of all, at time 0, how high is it?
0.
0. And then how do I know how high it is after 1 minute?
18.
Oh, is it in the bubble? And it's in Brody's head. Although it is...
It's in the problem. It says
in the problem.
1,800 feet per minute.
Okay, so 1,800 feet per minute we were given in the problem. So after 1 minute, what do we have? 1800. How about after 2 minutes?
3,600.
How'd Jerry get that?
Multiplied by 2.
Multiplied by 2 after 2 minutes, twice as high, right? Here's 1 minute, here's 2 minutes. All right, right now at your table with the people around you, you're going to fill in the rest of these values down to the 5th minute. We'll talk about what to do with this expression at the very bottom. You have a calculator. We already said maybe multiply is an operation that'll help you out. Mr. Craig and I will walk around. I think this will take 1 minute. Ready, go. You guys, there's 2 more calculators out there. You got 1, but maybe you need one on this one. Oh, you already got it? Okay.
Yeah.
Looking good. So far, so good.
It's 60.
Sometimes you gotta do both. You're gonna want a calculator. I love it that you're digging into the math, but life would be a lot easier if you could use your phone.
What about for
It's different than what other people have. Double check. And it's different than yes. 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 What did you multiply by? Okay, well that would be true if it was going up by a whole minute each time, but take your blue and it's a curve for you. Those look good. Alrighty then. Take a look up this way. Here we go. 2.5. Christopher, what do you have?
He's not here.
Oh, Chris, what do you have?
4,500.
Thank you. Myra, after 3 minutes, how high? 5,400, okay. Brody, you got 3.5 minutes?
6,300. Oh, I failed.
Okay. And 5 minutes, Andy.
9,000.
What?
9,000.
9,000. Do you agree with these numbers?
Yeah.
Now, as I walked around the room, they did throw a curveball in. So some people were adding 1,800. That worked right here. But when you didn't go up by a whole minute, you're not going to go up a whole 1,800, all right? So you could, in your head, if you like addition, say I need to add a half of 1,800. But what was the pattern of math that turned out to be easiest, especially as you got bigger and bigger down the table? Multiplication. That's what we're going to have right here in our expression at the bottom. For every minute or for every time t, we can figure out what the dependent variable is by going 1800 times t. Okay, so a very last box is the pattern that most people got to eventually. First, you could add, but after a while, it's better to figure out, I've got a calculator, what am I going to do with this thing?
It's 2.5.
4,500, is that what you're saying?
Or no, I was asking what T was.
T can be any amount of minutes. It's a variable. So it is, they gave us some T's, but this expression means we could figure out what's happened after 10 minutes. Right now we've only got up to its first 5 minutes. So a variable means there's options of T that might get plugged in. Maybe you need to know what's happened after 10 minutes, 15 minutes, 20 minutes. Okay? Write an expression in the last row. We already did. Explain how you determined the expression. How did we find that 1800t? What did we notice as we worked our way along that table?
Says it in the problem.
Okay, one thing we figured out is it says it. What it does it say in the problem?
18,000.
The rate.
The rate
The independent and dependent.
of 18,000 per
Your thing shut off that way.
minute. Okay, thank you. Okay, per minute in the problem. And why did we decide to multiply, to ultimately make an expression with multiply? So that was how we got started. But some of us started adding and some of us started timesing. Why did timesing turn out to be a better way? Molly?
Because it's going at a constant rate, so after every single minute, it would be doubling or tripling in constant.
Okay, so we were able to use the constant rate idea. Yes, Sam?
Instead of having, let's say you have 100 independent quantities, if there was 100 minutes, then it would be a lot better to just multiply 1,800 times your expression, your variable, and instead of adding it.
Okay, some people were listening. Sam said a great thing. What Sam is saying is adding work to good down here with low numbers, but if you had 100 or a big number, that would be 1,800 plus, 1,800 plus, 1,800. That would be a lot of adding, right? Multiplying really helps you jump steps to something bigger. So multiplication is easier with big times. So when we're working with 1, 2, or 3 minutes, we could just add, but we made this expression that we can use with small numbers and with bigger numbers. Nice. You ready for me to flip, or are you writing that down? Okay, next page. See how we're doing on time here. Good time to pause.